Hi, welcome back to Organic Chemistry. In this section we're going to look at ketones and aldehydes, but we're going to go pretty quickly because this material is almost completely a review of stuff that came in previous sections. First up, just a little bit of naming. Ketones, of course, are functional groups, are compounds that involve a carbonyl with carbons on either side. Aldehydes are something that are compounds with a carbonyl with both a carbon, with at least one hydrogen. Methanol, which is also known as formaldehyde, has two hydrogens. But otherwise, aldehydes have one hydrogen and one carbon group. The naming of ketones is fairly straightforward. You name them like alkanes. You pick out the longest carbon-carbon chain. But you change the ending to ONE to say that it's a ketone, and you have to say where that ketone is. So this example, 2-pentanone, is a 5-carbon chain with a ketone at position 2. An aldehyde, by definition, the CO double bond is at the end of a chain, so you change the suffix to say it's an aldehyde. Pentane becomes pentanal, but you don't have to say where that is, because by definition, where that aldehyde is, because by definition it's at the end of the chain. It's position 1. There are some common ways of naming ketones and aldehydes. An older way of naming ketones was by naming the carbonyl with the carbon chains on either side. So methyl ethyl ketone is a carbonyl with a 1 carbon chain on 1 carbon fragment on one side and a 2 carbon fragment on the other side. 2-propanone is better known as acetone. That's what we wash our glassware with in lab. Formaldehyde and acetaldehyde are fairly common names that go back to earlier naming systems. Formaldehyde is related to formic acid, and acetaldehyde is related to acetic acid. Now, the most important thing to know about carbonyls, about CO double bonds, is that they are polarized, and therefore they have a partially positive end and a partially negative end. Nucleophiles will add to the partially positive end, and electrophiles, usually acid, will add at the nucleophilic end, the oxygen end. Something that we'll get into in a subsequent section, the enolate chemistry, deals with the hydrogens next door to the carbonyl, so the so-called alpha position. Those protons are acidic because when you deprotonate them, you form a resonance-stabilized enolate. Just another general thing is that aldehydes are in general more reactive than ketones. Hydrogens are not as electron donating as carbon groups, and so therefore there's less electron density around that partially positive carbon. Also, aldehydes are more sterically free than ketones in that the hydrogen takes up a very small amount of space, which means that other groups nucleophiles can come in pretty quickly. There's about 4 ways of making ketones and aldehydes, some of which we've already seen. You can make ketones and aldehydes from alcohols by oxidations, from alkenes by ozonolysis, from alkynes by the addition of water. That's all chemistry we've seen. I'll show it quickly, but it's old chemistry. You'll have to look at other previous sections, the alcohols, alkenes, and alkyne sections to see that. And then we'll also see a new way of making ketones and aldehydes, and that's from ketals by hydrolysis. Just to remind ourselves, we have a couple of different oxidizing agents, PCC and chromic acid. The basic difference between those is the absence or presence, respectively, of water. PCC is an anhydrous reagent, and chromic acid is a wet reagent. As you probably recall from our discussion of alcohols, and if you don't, you should go back and look at the video that I have up on alcohols, you can oxidize alcohols to ketones, aldehydes, or carboxylic acids, depending on the alcohol and depending on the oxidizing agent. PCC will oxidize things once. If I start with a primary alcohol, it will be oxidized to an aldehyde. If I have a secondary alcohol, it will be oxidized to make a ketone. A key mechanistic step involves this proton, loss of a proton in an essentially irreversible E2 elimination gives our oxidized species. Notice that we have a hydrogen at this position in a primary alcohol. We also have one in a secondary alcohol, but we don't have any hydrogen at this position with a tertiary alcohol. And so therefore, this key step, this irreversible step, cannot happen with a tertiary alcohol, and you get no net reaction. But primary alcohols can be transformed into aldehydes, and secondary alcohols can be transformed into ketones with PCC. Chromic acid is a wet reagent, and therefore some further chemistry can happen with primary alcohols. Primary alcohols with chromic acid do initially get transformed into aldehydes, but further chemistry occurs to make carboxylic acids. Secondary alcohols, on the other hand, are transformed into ketones in the exact same manner as they were with PCC, and chromic acid leads to no net reaction with tertiary alcohols, just as with PCC. Again, for a fuller description of this chemistry, go back and look at the alcohol video, where I went through these reactions in very close detail. Another reaction that's old for us is ozonolysis of alkenes. And if you want to go through this reaction in detail, again, go back to the discussion of alkenes where we walked through this. But when I treat an alkene with ozone followed by DMS, a series of steps will occur that will ultimately result in breaking that CC double bond in half and replacing it with two CO double bonds. So in this case, since I had hydrogens here and here, I had a methyl and a hydrogen. I make something with a methyl and a hydrogen. I made an aldehyde. If I had two carbon groups here, I would have two carbon groups here in the product. That would be a ketone. So we can make ketones and aldehydes from appropriately chosen alkenes and ozonolysis. Also, finally, for the completely review examples, if you recall from our alkyne discussion, and again, you could check out the alkyne video for details, if we had H and OH, so essentially electrophilic addition of water across a triple bond, you initially form an enol. And that enol is in equilibrium with the keto form. Series of proton transfers essentially leads to this. We can have the ability, depending on the reagent we choose, to add H and OH in a Markovnikov or an seemingly anti-Markovnikov fashion to put the oxygen on either the more substituted or less substituted position. If it's on the more substituted position, after ketoenol tautomerism, we get a ketone. If our OH is at the end of the chain, after tautomerism, we get an aldehyde. So this is a great way of choosing to make either a ketone or aldehyde from an alkyne. And finally, for making ketones and aldehydes, we can make them from a functional group called a ketal, or something like a ketal. On this list here, we see a ketone, and a ketone is related to either, this is called a ketal, and this is called a hemiketal. It's kind of a half of a ketal. This is an aldehyde. Aldehyde is related to an acetal or a hemiacetal. And these species could be hydrolyzed to make, respectively, either an aldehyde or a ketone. So, for instance, if I took this ketal and I treated it with acid and water, a reaction would occur to make the ketone, and these two equivalents of alcohol would be produced as well. We'll actually see that in just a moment in detail, so I'm going to hold off on the mechanism for a moment. First, I want to look at the reactions of ketones and aldehydes. Mostly, the reactions of ketones and aldehydes involve strong nucleophiles. A lot of examples that we have led to the formation of alcohols. The Wittig reaction also included a strong nucleophile adding to a CO double bond. We're going to see that weak nucleophiles, like alcohols, under acid-catalyzed conditions could lead to ketals. So that's where I'm going to go through that chemistry specifically of ketals. And then finally, aldehydes, it turns out, can be further oxidized to make carboxylic acids, as we'll see. So just remind ourselves, nucleophilic additions to ketones. When I have a very strong nucleophile, and a Grignard is an example of a very strong nucleophile. A Grignard behaves essentially as a carbanion. Well, a Grignard or other strong nucleophile will add to the partially positive end of a ketone or aldehyde, pushing electrons up onto oxygen. And this species, if it gets then in a subsequent step protonated, will make an alcohol. Lots of different strong nucleophiles exist. We focused on hydrogen-based nucleophiles, such as lithium aluminum hydride and sodium borohydride. These are both essentially sources of H-, or carbon-based nucleophiles. These are things that either are carbanions or behave as carbanions. Grignards and alkylithiums behave as carbanions, but we can also form carbanions from terminal alkynes, as we discussed in the alkyne chemistry section, or from ketones, the position next door to a ketone. Those hydrogens are acidic and can be deprotonated to make the enolate, which will be covered in a subsequent section. Just starting with some of the simple nucleophiles like hydrides and Grignards or alkylithiums. We can use these to make whatever alcohol we want, depending on if we start with ketones or aldehydes. If I started with a ketone, and I added a third, so a ketone has 2 carbon groups here. If I added a third carbon group via Grignard or alkylithium to this position, electrons go up, protonate, and I get something with 3 carbon groups. That's a tertiary alcohol. If I started with a ketone and I added a hydride adds here, electron up to oxygen, protonate. Well, this is a secondary alcohol because it started with 2 carbon groups and I added a hydrogen group. So I got 2 carbon groups and a hydrogen around this carbon. That's a secondary alcohol. I could also get to a secondary alcohol if I started with an aldehyde. Here I have a carbon and a hydrogen. If I add a carbon via Grignard, I'm going to also get a secondary alcohol. And finally, if I started with an aldehyde and that's got a carbon and a hydrogen, if I add another hydrogen, well, I get this kind of thing that's got a carbon group and 2 hydrogens. That's a primary alcohol. We can really make any alcohol we desire, depending on a judicious choice of ketones, our ketones or aldehydes as starting materials, and either carbon-based nucleophiles or hydrides. Another reaction that we saw previously, this in the alkene chemistry, was the Wittig reaction. A phosphorus ylide species will add to a carbonyl, and mechanistically that involves the anion from the phosphorus ylide initially added to the carbonyl carbon, electrons getting pushed up onto oxygen, and then that O- reaching across and connecting with phosphorus, forming this 4-membered ring. It's called a phosphooxetane, which will fall apart to make an alkene. And now finally something a little new. If I take a ketone and I treat it with 2 equivalents of an alcohol, under acid-catalyzed conditions, I will make that ketal plus water. It turns out this is a reversible process, and it's driven by Le Chatelier's principle. If I was to take a ketal plus water under acid-catalyzed conditions, I'll make a ketone plus 2 alcohols. That's the reaction that I mentioned a little bit earlier. How does this work? Well, if I've got ketone and alcohol and acid, it turns out one thing that can happen, and the most likely thing to happen actually, is that the ketone gets protonated to form a carbocation. This carbocation is very electron poor. It wants electrons. Somebody has, oh, those alcohols have electrons. So oxygen can act as a weak nucleophile, adding at this position. After loss of proton, we get a hemiketal. This is halfway to the ketal, so we're not quite done yet. We're still under acid-catalyzed conditions, so we can protonate either of those oxygens. If we protonate the one that I've highlighted in blue, we're going to go back to the left, but these are all reversible steps. And so that's all fine. This is going to be driven by Le Chatelier's principle. But if I protonate the other oxygen, I make water, which is a good leaving group. So if that leaves carbocation, have another equivalent of alcohol attack, and loss of proton leads to the ketal. Notice that the reverse reaction is also possible. I could have started with the ketal, protonated, making this intermediate, breaking this bond, loss of ethanol, leads to this intermediate, water attacking leads to here, loss of a proton to here, the hemiaminal, protonation of the blue oxygen, breaking of an ethanol, a carbon-oxygen bond to lose ethanol, and then loss of a proton leads to ketone. So I can go either way. I can push this from ketone to ketal or from ketal to ketone based on my conditions. Notice ketals and acetals alike, you really can't stop at that central hemiacetal. Because if I have an excess of alcohol, I'm just going to keep on pushing. Le Chatelier's principle will take the ketone initially to the hemiketal, and then again further reaction onto the ketal. And since alcohol is involved in each of those steps, if I have an excess of alcohol, I'm going to go from ketone straight onto the ketal and never stop at the hemiketal. But there is one case in which we can stop at the hemiketal. Or in this case, I'm going to show stopping at the hemiacetal. The only difference is if ketal would involve a carbon group here, like a methyl maybe. But I'm going to choose to make a hemiacetal for a reason that will become apparent in a moment. But if I treat this acid, well, I can protonate. And here, there's an alcohol that's part of the same molecule, right? I've highlighted the other end of the molecule in blue. That OH behaves like an alcohol. I mean, it is an alcohol. So it can reach over and make a bond. In fact, an intramolecular reaction, such as this, can in many cases be more favorable than an intermolecular reaction. That's a reaction between two separate molecules. And after loss of proton, we get, well, this is technically a hemiacetal. Because at this position, we've got an O carbon, an OH, a hydrogen, and a carbon, which is what we see in a hemiacetal. Now here we do stop at a hemiacetal. Why? Because by definition, we have exactly one equivalent of our alcohol for every one equivalent of our aldehyde. It's so, excuse me, each molecule will react with itself internally to make a hemiacetal in this case. Now, why is this one interesting? Well, if I was to put some other OH groups on my initial species, I'd get a cyclic product that also has several OH groups. And, well, this is a sugar. Glucose has this structure, just with some stereocenters put in. And glucose, for instance, exists in open chain and cyclic forms. So in the body, we will see an equilibrium between the open form D-glucose and the closed form D-glucopyranose. But the chemistry of this is just sugar cyclization. Sorry, this is sugar cyclization. The chemistry of this is just hemiacetal formation. It's exactly the same chemistry. This can actually cyclize in a couple of different ways to make stereocenters at this position where this OH is either down or up, and that has to do with when this oxygen reaches over to attack. There's rotation around this bond. Which orientation you get will lead to different ones. Since the beta anomer and the alpha anomer, which those were called, are both in equilibrium with the open chain form, they are also in equilibrium with each other via the open chain form. And this process in the body is called mutarotation. If you protonate the blue oxygen, break a bond, you get a carbocation, do some conformational change. That is essentially just rotation around this carbon-carbon bond. So this OH rotates up, and then closing back up and loss of proton leads to the product. And this is just opening up a hemiacetal and then closing it back up again. Also important in the body is glycosidic bond formation. If I take a sugar and I treat it with an alcohol, under acid catalyzed conditions, I will make what's called a glycosidic linkage. I'll put my alcohol here. Now, how does that work? If you do a little bit of a careful study, you find out that the oxygen that's incorporated into the glycosidic bond comes from the alcohol. Mechanistically, this whole thing works by, well, protonation of an to make a good leaving group, loss of that water as leaving group to form a carbocation, and then an alcohol, loss of proton. If you look at this closely, you'll realize that this is just going from the hemiacetal to the acetal. So this is just part of that acetal formation mechanism. It's just kind of the second half. Now, methanol is interesting as an alcohol in here. But what if we, instead of having methanol as our nucleophile, what if we had another sugar? A sugar has a bunch of OH groups, so we could just simplify this and think of this as just a big alcohol. I mean, it's got a bunch of alcohols, but let's just focus in on this particular OH. If this comes in and makes a connection here, now we've made a disaccharide. A disaccharide has got two sugars. But we could do it again over here and make a trisaccharide, or eventually we could make a polysaccharide. Starch and cellulose are two very important polysaccharides. Just a couple other quick things while we're talking about ketals. One thing you will often see, instead of using two separate alcohols to make your ketal, so if like ethanol, two equivalents of ethanol is the example I used before, sometimes we'll use a diol, in this case ethane diol, but you'll also see propane diol, to make a cyclic ketal. And chemically, this is exactly the same as the other. It's just, instead of having 1 mole of alcohol add, and then later on having a second separate molecule add, this involves having one alcohol add, and then after loss of water, the other oxygen wraps around and adds as well in an intramolecular fashion. And you can do that with oxygens, or you could also do that with sulfurs. These thioketals, that's the sulfur version of a ketal, can be hydrolyzed, just like ketals can be hydrolyzed, though their conditions are a little bit different. Acid and mercurium, mercury 2, will get rid of this and replace it with a CO double bond. Just like ketal can be treated with acid and water to make back a ketone. But another good reaction is you could reduce away these bonds. If you broke these bonds with hydrogens, hydrogen and Raney nickel, that's a heterogeneous catalyst, we'll just get rid of the sulfurs altogether. Thioacetals can be formed from aldehydes. I'm not going to belabor this point, but the same chemistry. But this thioacetal, it turns out this proton's kind of acidic. And so with a particularly strong base, like butyllithium or maybe LDA, you could deprotonate this position and make the conjugate base, which can then act in this example as a nucleophile in an SN2 process to add new carbons to this. And then this thioketal could be removed either by hydrolysis with acid and water and mercury chloride, or we could just reduce it away with hydrogen and Raney nickel. Finally, in the reactions of aldehydes specifically. Now, for most things, aldehydes and ketones behave the same. But aldehydes were an intermediate in our chromic acid oxidation of primary alcohols. If we started with a primary alcohol here, it would undergo a series of steps, formation of a chromate ester, irreversible E2 eliminations to form an aldehyde, but we're still in the presence of wet chromic acid, so we can have more equilibria to form a hydrate, which will react with the chromic acid, to keep going on and on and on to ultimately make a carboxylic acid. What about this? What if we just started with this? You know, if I start the ball at the top of the hill, it'll roll to the bottom. If I start from this point, I'm going to go on to the energetically favorable bottom of the hill. But what if I started halfway down the hill? If I set the ball halfway down the slope, it's still going to roll down to the bottom, because this, in the presence of wet chromic acid, will go on and do all these steps. And so aldehydes, since they're an intermediate in the process of primary alcohol oxidation, they could also be a starting material. So if you treated an aldehyde with with acid, water, and chromic acid, well, that will go on to the carboxylic acid. That does not work with PCC, by the way.